All right, hello everyone. So today we're gonna discuss the non-inverting op amp. Right? Last time we discussed the inverting one. Let's discuss this. Its counterpart. So this one is a bit different. There's one difference actually. The cell previously in the inverting op amp, it was here, right? Uh, it was I didn't label these. This is the inverting input, this is the non-inverting input. The cell previously in the inverting op amp, it was here leading up to the inverting input, you could say, but now it's directly connected to the non-inverting input. All right. Yeah, so this is the non-inverting op amp, and well, we'll see why it's called non-inverting in a bit. Let's try to solve for it. All right. So let's see. Well, again, when I say solve for it, I mean find um, V output as a function of, the supply voltage. All right. So, uh, first thing first, we see that at the non-inverting input, the potential, the voltage, this is going to be our V2. This is equal to Vs, right? Right. So because this is the ground, we have a cell here, so this is Vs, right? And since we know this is an ideal op amp, okay, we're assuming it's an ideal op amp. This is also going to be Vs. Our our inverting input also has to be Vs, right? That was one of our conclusion. That was one of our conditions that we got after assuming the necessary assumptions, you could say, for the ideal op amp. So this is also Vs. All right. Now what can we do? Well, let's do nodal analysis here. But before that, let's see what's happening here. We have, let's see, we have a current that's let's say it's going here. Okay. We have another current here, but that is zero. Okay, as we know, the input currents are zero. And let's say we have a current entering here. Let's say there's a current entering here. Okay. So all right, what we have is this current going into this node. Okay, if we consider this node and apply nodal analysis or KCL here, the current entering this node has to be the current equal to the current exiting here. Okay, so this is equal to this. All right, so what is this current? This whole node right here. Okay, this whole node right here, this is the ground, right? So the potential is zero here, right? So zero minus yeah, oh sorry, yeah, I kind of misunderstood. The current here is zero, the voltage is Vs. Yeah, it's not. Yeah, so 0 minus Vs divided by R1. Yeah, 0 minus Vs divided by R1. Let's write that down. So the current entering that node is 0 minus V sub s divided by R1, and this is equal to the current exiting. This one doesn't matter, and this one is let's see, Vs minus the potential here is V output. Okay, so Vs minus V output, I'll write that here. This is V output divided by R sub F, right? The feedback resistance. Okay, so this is equal to V sub S minus V sub V output divided by the feedback resistance R sub F. All right, now we are almost done. Let's try to solve this. Well, we are trying to solve for V output, so let's multiply both sides by the feedback resistance. Okay, so we have negative R sub F divided by R1 equals V sub S minus V output. All right. Now, if we bring V output to this side, wait, no, there's something as there's something really wrong here. So this one you had a V sub S, the supply voltage here. Okay, that's a factor here. All right. So if I bring the output voltage here and I bring this term here, okay, what I get at the end is, it's very simple algebra. What I get at the end is V output equals 1 plus the feedback resistance divided by R1 multiplied by our supply voltage. Now this is our result. Um, this is what we aimed for. Our output voltage is a function of our supply voltage, and as you can see, there's one really important thing, which is from where this op amp gets its name, is the voltage isn't inverted. Okay, the output voltage isn't inverted compared, with respect to the input voltage. There's no negative sign here, and this has to be positive, right? The resistances are positive. It's very obvious that this factor is positive. All right, so and if you want to know the gain, it's pretty easy to find that. If you just need to divide by V supply. So your closed loop gain is 1 plus the feedback resistance divided by that R sub 1, the other resistance that's connected here. So this is your gain, and this is basically your output voltage in terms of the supply voltage. So that's the formula. Now let's try to do some problems with this. And unlike last time, I did some very obvious, very obvious problem to begin with for the inverting op amp. Let's try something a bit more interesting, just to test ourselves. So the first one, and this should also clear up, if there's one certain, well, I wouldn't say misconception, but the first time I think that many people, me included, see this, it's just a bit, uh, confusing. So let's try to clear that up. So let's say this is 4 kilo ohms. This is 8 kilo ohms. Whoops. This is, okay. So you have this, you then have, okay, now it's, they clear, the problem clearly shows that this is the non-inverting input on top, okay? So, that's that, if they have given that this is on the top, then it is, uh, but usually the inverting input is drawn on the top, but it's not necessary. That's all. It's not necessary. So there's one resistance here. This is 2 kilo ohms. This is 2 kilo ohms. This is, and this is 5 kilo ohms. All right, and this is your output terminal. This is your output terminal. Yeah, yeah. So this is negative V output positive. So again, we need to find V output. All right. So at first glance, this doesn't look very much like our non-inverting op amp, but let's try to consider some things. All right. The first thing I'd like you to notice is actually the things at this end, the inverting input. They are actually the same as, the configuration is the same as here. It's just drawn a bit differently, but it's pretty clear that this is actually your feedback resistance. This is slinged over the op amp, right? This is slinged over the op amp, and then you have this connection with the inverting input. You have this resistance, after this node you have this resistance here, okay, 2 kilo ohms. That's your R sub 1. So I'll write that down. This is your feedback resistance. This is your R sub 1. This is your R sub 1, and then you have, and we could assume that this is the ground. So that part matches, our diagram, but this one it's not that obvious that, whether it does or not. So we cannot say this is an non-inverting op amp yet, but let's consider something. This is interesting, and for what I mainly picked this problem. Okay, so what's the current here? Zero, right? So this is the current entering, one of the op amp inputs. So this is zero. This is an ideal op amp. So, and if this is zero, and if we are considering this loop, this loop right here, well, I'll mark it like this. if you're considering this loop as a closed network, okay, this current here is 0, so there's no current going from here. What is the current here? What's the current here? Well, this has to also be 0, right? Whether you call it entering or exiting, this has to be 0, right? Because you have a closed network, there's no current from this end. If you have just one path for the current to flow, it's actually not going to flow, right? Because a closed network, it cannot gain or lose any current, right? According to KCL. So the current here also has to be 0, like this one. Well, if both of these currents are 0, this loop is actually just operating by itself, right? This is just an independent loop, okay? This is just a 9 volt, uh, a 9 volt cell connected to two resistors, 4 kilo ohms and 8 kilo ohms, which are in series, right? That's all that this loop is. This loop is independent from the rest of the circuit, right? So if that is the case, we can actually use everything that's true about series circuits and resistors. So if I want to find, like, see here, what's our V2? This is, this whole node, right? This whole node is, I should pick a different color for that. Let's see. This whole node right here, right? This is the same. This is the same, and the voltage here is going to be our V2, our non-inverting input. And to find that, what we would like to do, this would be the same as the uh, voltage across the 8 kilo ohm resistor, right? This has to be the same as the voltage across the 8 kilo ohm resistor compared to the ground, we see. So and as we said, this is just your plain, series circuit loop, and thus, we can just apply our voltage divider rule to find this voltage, right? This voltage, this is going to be V2. This is going to be V2, right? We can just apply our voltage divider rule, right? So V2 is going to be equal to, well, the one that we're concerned with is 8 kilo ohms out of a 4 plus 8, which is 12 kilo ohms. So 8 over 12, 8 over 12 multiplied by 9, and this is going to be 6 volts, right? 2/3 into 9, yeah, that's 6 volts. All right, so if this is 6 volts, so we have here the our non-inverting input, that's 6 volts, okay, and this one matches, our non-inverting our non-inverting input circuit, okay. This one is 6 volts, which is directly the input of our non-inverting okay, directly the voltage of our non-inverting input. This actually is the same as this, okay. One thing we need to realize, that it's not necessary that a cell is directly connected here. All that's necessary is we have some voltage here, okay, and at the non-inverting input we clearly have uh, you know we clearly have the voltage stated here, okay. Doesn't matter that it directly comes from a cell or we get it like this, okay. It's really the same thing. It's really the same thing. So this whole thing, we could even just discard this part and say that, okay, so there's actually it might be a good idea to do that. This is exactly the same for our purposes. This is exactly the same as if we wait, I'll make that bigger, as if we discarded this part, okay, as if we discarded this part and said that, okay, so this is the same. Let's see, I'm adjusting the, okay, so this is the same as if we just connected 6 volts, a 6 volts uh, cell here, okay. This is exactly the same as that. And well, if it is, then, as I said, this is our non-inverting op amp. This is our non-inverting op amp. So let's apply the formula. Let's find our output voltage, which is what we wanted. So the output voltage is going to be equal to our, so yeah, and well, according to that, again, I'd like to say here too that your Vs is just your Vs is just going to be your the voltage at your non-inverting input. Doesn't matter if it comes from a cell or some other method. So you could again rewrite this formula. It's your V supply, or we just say your your V2. Okay, your V2. I'll do that in a different color, not that visible. Okay, so you could just say it's also your non-inverting input voltage. All right, it's really the same thing. It's really the same thing. It's really the same thing. All right, so enough with that. Let's now just find this. So this is going to be equal to, with that got erased. So let's see, 1 plus your feedback resistance. This is 5 kilo ohms. Okay, so 5 kilo ohms divided by 2 kilo ohms. Okay, your other resistance. So it's just 5 by 2, 5 by 2 multiplied by this voltage right here, 6 volts. This voltage right here, 6 volts. And this is going to be, if you calculate, this is 3.5 into 6. That's 21 volts. That's 21 volts. All right, so we got our answer. It's 21 volts. It was pretty interesting. Okay, the main thing what I wanted to show in this problem is we don't need to be stuck up on the fact that this has to be a cell. Okay, particularly this is just your non-inverting input. Okay, no matter how we got it. Okay, so let's move on. And this is another interesting problem. And this is basically what I want to show you, what you can do if you consider more than one configuration. And since we now know both the inverting and non-inverting inputs, so I felt that this problem is just comes at just the right time. It's pretty interesting. So 20 kilo ohms, um, and this is your op amp. This is 40 kilo ohms, your feedback resistance. This is your output. We need to find that. And this is your, oops. Okay. So this here you have of 2 volts. So this is my diagram. Now, this is interesting. The thing is, this doesn't match any of our op amps actually. This is not our non-inverting op amp. It's close, but the thing is we cannot have a cell here. Okay, cannot have a cell here. This is not your inverting op amp. We couldn't have a cell here. This has to be the ground. Okay, our virtual ground, you could say. If we wanted it to be, let's say this is the ground. So if we wanted it to be the inverting op amp, so it's not that either. All right, but and let's just consider one thing. What if this cell wasn't here? I'll erase this. Okay, so wait again. Let's see. I'll erase this for now, just for now, and let's say I think some of you might be seeing where this is going. Um, if you have studied superposition in particular, I think you see that what I'm trying to do. Okay, so if I just consider this circuit, let's say this is V output 1. Okay, I'm clearly revealing what I'm trying to do. The thing is, this is now a non-inverting op amp, right? Let's just find this voltage for now. Let's just find this voltage for now. This is V output 1. And actually, let me just say, I think this is inefficient, so let me just say what I'm trying to do. The thing is, your op amp, it's actually a linear circuit element, right? All the time we've been seeing that your output voltage is always, it's linearly dependent on your input voltage, right? So your op amp is a linear circuit element, and if it is so, it's we're allowed to use superposition, right? We're allowed to use superposition. That's what I'm actually trying to do. We saw that, if I just take this out, okay, if I just take this out, this becomes a non-inverting op amp. And okay, so I'll write this one. So this is non-inverting, non-invert. Oh, sorry. Have I been saying non-inverting? This is your inverting op amp. This is your inverting op amp. And if I uh you know keep this, if I kept that cell, took this out, I'll have to pause for a bit. All right, it's quite an. I hope much of the ruckus outside didn't reach you. All right, so and if we kept this cell and took this one out, this actually would be our non-inverting op amp. We'll see that in a bit. So what I'm trying to do is basically use superposition. All right, so if this is, if this is our inverting op amp, our um, output voltage is going to be negative. So this is our feedback resistance. This is the other resistance. Okay, so the output voltage is going to be negative, uh, 40 over 20, right? 40 over 20, the kilos cancel out, kilo ohms cancel out. 40 over 20 multiplied by 6, right? 6. So this is going to be negative 12 volts. This is going to be negative 12 volts. All right. And in the same way, if well, first I'll need to erase that. First I'll need to erase this. Let's see, I'll make this big. Erase this portion to 2 volts. This was 2 volts. This is actually now our instead of inverting, this is a non-inverting. Oops, what happened? Okay, this is the non-inverting op amp. This is the non-inverting op amp. All right, and if that's the case, we can just use the formula. So now let's call that instead of V output 1, it's V output 2. I'll actually erase this. So V output 2. Okay, so this is going to be this is going to be 1 plus feedback resistance is 40, the other one is 20 multiplied by, and this voltage is actually 2. This voltage is 2. Okay, so this is going to be, let's see, 3, right? 3 into 2, that's 6 volts. So now, what we were waiting for, what all this was for, is our output voltage, our, combined output or actual output voltage is just the superposition or addition or the sum of these two individual output volts which we got from turning off one cell and keeping the other one on. So this is going to be negative 12, just our basic superposition. This is going to be negative 12 plus 6 or negative 6 volts, negative 6 volts. So very interesting, we got our result by applying both the op amps that we have seen so far, both the types, and that's why I think this was pretty interesting. One more thing is, actually you can solve this even without those two. Okay, even without knowing these two, and I feel like this is mainly I just wanted to show you that you can use superposition and all that, because this is your op amp is actually a linear circuit element. But I this problem is actually easier if you just use. Oops, that didn't change to yellow. This problem is actually easier if you just use just treat it as a single, or treat all of it at once. Okay, just as an ideal op amp. If you try to do it that way, and I'll actually do that because we got a bit less practice with just ideal op amps. Okay, so let's see. So this is 2 volts. This is 2 volts. This also has to be 2 volts, right? The input voltages are the same. Now, if we consider the currents here, it seems like this node might be the most important for us. Okay, so there's a current entering here. Okay, this one is 0, and there's a current exiting here. Okay, and this is V output. Okay, so if that's the case, what we have is the current entering is equal to the current exiting. Okay, so 6 minus 4, 2, 6 minus 2, that's the voltage difference for the current entering, divided by our resistance, which is 20 kilo ohms, 20K. This is equal to our current, which is exiting, which is 2 minus V output, 2 minus V output divided by 40 kilo ohms, 2 minus V output, 2 minus V output divided by 40 kilo ohms. All right, so if we multiply by 40K on both sides, we get it. So this is 4, and we get let's see, 2, 4 into 2, that's uh, 8. Yeah, 8 equals 2 minus V output, or V output equals 2 minus 6 or minus 6 volts. So this is actually the easiest way to do it. Okay, I'll have to admit, but the purpose of me going this way is just to show you that you can apply superposition on your ideal op amps or your op amps in general, actually. uh, And yeah, and just to see the usefulness of the two types that we have learned so far. But anyways, so that's the end of the of this video. We're gonna look at the summing of amp next, I guess. And yeah, I've been forgetting to say this the next few, sorry, the last few videos. But if you like this video, if you found it helpful and appreciative, please do leave a like and please do subscribe to this channel. I really appreciate the support and don't know if I can go without it. So yeah, please do keep supporting the channel, and yeah, goodbye, study smart.